Okay. So we're recording. I'm going to talk about exploratory data analysis. I just have a few slides, then I want to go into the code. Exploratory data analysis was a term coined by Chuki in 1977. And basically, his idea was that there are two things you might want to do. Basically, the goal of your study of your data is often to build a model which might be some kind of hypothesis test, as it was in those days usually, or nowadays often a predictive model. And that was one kind of data analysis, building a model. And he called that confirmatory. And then the other kind of data analysis is exploratory, where you just look at your data and find out about it. What have you got? And it's very important to do this. Even if your goal is to do a predictive model, you really need to look at your data. So today I'll be explaining how to look at your data. The goals of doing this, or the things you should be looking for, are to get your data cleaner. So often the data will arrive in a fairly clean format, like the one I'll show you today, but often not. So often it will be very messy and you have to clean it. But even if you've done that data cleaning step, you'll still want to do some more exploratory analysis because often it won't be as clean as you thought. You want to visualize the data you have. You want to look for outliers usually because those can often spoil your models. You want to prepare the data for modeling. So for example, if you want to put your data in a linear regression, you can't do it if you have some missing values. So you want to look for those and maybe decide what to do about them before you start building models. And then also often from exploratory analysis, you can find out new questions. Even if you had a question in mind at the beginning, you might find some new interesting things, like we'll see today some interesting things in this data set that I'm going to show you. An important thing to note about, two things I want to note. So one thing is that people will often tell you stuff about the data when they give it to you. And in my experience, these things they tell you are often not true. So even if you've been told stuff about your data, you should still check that it's true. So sometimes that can ruin your analysis. And the other thing I wanted to say is that when you're doing predictive modeling, often you want to hold out some data and test your model on that test set. And when you do that, you should always replicate all the steps of your modeling process on that test set. And that includes technically the exploratory analysis. So some people will go really extreme and say, before you even look at your data, you should throw some away at random and use that as your test set at the end. Because then you can guarantee that everything you did was completely independent of your test data. But that's quite an extreme position, and mostly the benefits of doing the exploratory analysis outweigh any little problems you might have from not separating some test data at the beginning. So I do recommend always doing exploratory analysis on all of your data, even though you're going to separate it into training and test later on. So you will sometimes meet fundamentalists who would disagree with that position, but I think that's what you should do. So that's basically what exploratory analysis is. So how to do it? So you should work in a REPL or shell or whatever you want to call it, which means just a thing where you can type in code, it will give you the result, and then you can type in some more code and go like that. So you can do this in R, Python, Julia, any of these languages, but exploratory analysis is best done in that kind of situation. So you don't want to use Java or C or some compiled language to do your exploratory analysis. You want to have something that you can use like a calculator. I recommend making a lot of plots, so that's really important. In my experience, the best way to start is to go through each variable in turn and do an analysis just of that variable, so univariate analysis. In the past, I've had situations where I was, for example, studying education and salary, and I didn't do this, and then it turned out after the model had been built that actually the data wasn't quite what we thought. And if we just done this univariate analysis step at the beginning, we would have known, but we didn't actually find out until later, and then we had to redo the model. So I would say it's quite important to go through each of the variables, plot, or somehow look at each one individually. And then after that, you can start doing bivariate and multivariate analysis, where you look at combinations of variables and do some more plotting. And you can find out some very interesting things. Some people, so at the beginning I said that there was meant to be a distinction between exploratory and confirmatory. And confirmatory is where you build the models. But I think that models can also be a very important part of exploratory analysis. You don't have to use models to do a statistical test or a grandiose prediction. You can also use them as a way of looking at your data or simplifying it. Even the box plot I would regard as a model, where you're just saying that the distribution of your variable is being approximated by this a lump of probability mass and then some tails. So everything is a model, really. So you can definitely use models as part of your exploratory analysis. So the data set I want to look at today, I'll be using Python for the exploratory analysis. And this data set contains various different types of data. So we'll look at how to deal with numerical variables, categorical variables, and then things like dates, which is kind of ambiguous. It could be numeric or categorical. And I was asked to get a data set related to insurance. So what I've got is a data set of complaints about insurance companies in Connecticut. This data set is provided by the Connecticut state government on their open data portal. And I don't have a huge amount of information about this data set, but I think each row of this data set is a single complaint. And there's some information about the complaint. And then the variable of interest probably is how much money was paid out to the person who complained. So usually it's 0, but sometimes the complaint has been upheld, and we'll see that they got some money from their complaint. So that's probably what we should be looking at. And slide 4, this is the last slide. I'll just discuss this one at the end, some suggestions for further reading and how to learn exploratory analysis. So now I'm going to go on to the Python script. I'm going to run this live, so I hope that it will work. Sorry, the text is a bit small there. Might be able to make it bigger. No, it doesn't work. Okay. So I'll just keep it this size. Hope you can read that. So to start off, I'm just going to import some libraries. Pandas. The only function from the math library I'm going to use is log, numpy, seaborn, which is the graphics library, and matplotlib, which is the other plotting library. So the data has been provided as a CSV file. That file is not directly available online, so it has to be accessed by an API, which is why there's this API call here. But we should be fine. And I've just made it print out the number of rows and columns in the resulting data frame. So we've got 18,112 rows and 12 variables, which is a very small number of variables, actually, but enough to get a good feel for what kind of thing we should be doing in exploratory analysis. You should always start off by just looking at some of the data. So let's look at the head of our data frame. So we can see what we've got here. So each row like I said, corresponds to a complaint, I think they've got this file number, which I suspected would be a unique identifier, but we'll see later that it's not a unique identifier. We've got when the complaint was opened and closed, so those are date variables. That's presumably opened is when the person complained, and closed is when the complaint was resolved. Coverage is going to be what kind of insurance they had. Sometimes it's missing, as you can see. Subcoverage is presumably a more detailed description of the insurance. Reason is why they're complaining. Sub-reason is, again, more specific reason. Disposition, I think, well, actually, I'm not sure what that is. It's probably something to do with what happened to the complaint. Conclusion is the same thing, what happened to the complaint. And recovery is the amount of money that was paid out in the end. So here, company position upheld means that the insurance company was held to be in the right. It was unjustified, the complaint, so they got no money. And then the last column here, which you can't see, is status, which is, well, we'll see in a minute. So in this comment here, I've said that the data frame has 18,045 rows, but it now has 18,112. And the reason for that is because it's actually a live data set that's being updated. It's seemingly every day, because I've been running this the last couple of days, and it's changed every time. Let's just look at the names of the columns. So I'm just printing this so we can see what we've got. We've got these 12 columns. We saw them all except status above. And then the first thing I want to do before going into the variable by variable univariate analysis is to check whether there are missing values in the different columns. So what I'm doing here is applying this function to the data frame, and this function lambda x is doing x.isNA. That's the so for a series x, that's going to make a vector of trues or falses depending on whether the value of x there is not a number, and then it adds up how many NA values there are. So this line here is just counting the number of NA values in each of the variables in the data frame. So we can run that, and we see that for some variables like the name of the company or the file number, there are no missing values, and then for some of them there are quite a lot, especially the subcoverage variable. So you can see from this, we have 18,000 rows in the data frame, and there are almost 12,000 missing values in subcoverage. So that means that if we're building a predictive model using this data, probably we're not going to want to use subcoverage because it's just not, it has too many missing values. So that's useful information. So it's always good to look at how many missing values you have and where they are. Another thing we might want to do before we start getting into exploratory analysis is to check whether there are any duplicated rows, and that this line just dat.duplicated is a vector, a series that is true or false depending on whether a row has been seen earlier. And then we add up how many trues there are, and there aren't any. So actually, there are no duplicated rows in this data set. So now I want to go through the variables one at a time, starting with the name of the company. So the company name is a categorical variable, and with categorical variables, usually you want to see, you just want to do a count of the different values initially. So we want to see here how many times each company appears in our data set and how many companies there are. So we can just print that out, and we find that there are some companies appearing a lot, particularly Anthem Health Plans, Inc., which has an enormous number of complaints, far more than any of these others. And then there are quite a lot of companies with quite a few complaints. And then we have, looks like a long tail of companies with just one complaint at the end here. So that's the value counts function, just counting the number of times each value occurs. That's what you usually want to do for a categorical variable. And then the length of that value counts is the number of companies that are. So we can see how many companies are represented, and 672 in total. That's useful information because if there were, for example, 5 companies, that's a very different kind of categorical variable to one with 672. If there were just a small number of companies, when we're building a model later on, we could have we could one-hot encode each of the company names. But if we have a situation like this with 672, we can't do that. So we have to deal with this company variable probably in a different way. Then we can always visualize what we have using a bar chart rather than just a table of values. But we don't really want a bar chart with 672 columns because that looks horrible. So I'm just going to plot the first 30 companies. I've got a 1 there by mistake, so it's companies number 1 to 30 should be companies number 0 to 30. The reason why I'm starting from 1 there is because I'm usually using R, and R indexes vectors starting from place 1, whereas Python starts from place 0. So if I just do that, it will start. It will go from the top 31 companies, and then for those companies, I'm plotting a bar chart of the number of complaints, and we can see that Anthem Health Plans has a vastly higher number of complaints than any of the others. These two have slightly more complaints than the next few, and that seems to be going down. I like that. It's kind of interesting because I would probably have expected, just from experience, maybe that the number of complaints would follow something like a power law. But this is not a power law, it's a different kind of distribution. So it's kind of interesting to me. And then we can look at also, we can make a histogram of the number of complaints by companies, which is just looking at the height of these bars and seeing how many bars we have of each different height. And if we plot that, it's pretty rubbish because we have 1 with a huge number of complaints over here, and then a lot with a small number. So when you get a histogram like this that looks a bit rubbish, often it's a good idea to apply a transformation. So here I'm going to apply a log transformation to the number of complaints and get a more useful histogram. So I chose to use log to base 10 here because it's easier to interpret. So a 0 on a log to the base 10 scale means 1, and 1 means 10. So we can see actually this histogram is slightly interesting. So there's a very large number of companies here at the bottom with just 1 complaint. Then there's kind of a dip, and then it gets to companies with 10 or more complaints. So that's kind of interesting. So it looks like there are 2 types of company. One type is the ones that have been seen very rarely in the data set, and then the others have been seen quite a few times, at least 10 times. So that was the first variable, the company name, and now let's look at this file number. So I thought the file number might be a unique identifier, but actually it's not. So remember, we had 18,000 rows. We only have 14,000 file numbers. So I looked at one of the file numbers, and it seems like for this file number, we have various different insurance companies and different kinds of cover, but all the complaints have been opened on the same day. So it makes me think that maybe we're looking at just a single complaint here, but for some reason it has different file numbers. So I would like to find out more about this file number, because it looks as if maybe the rows of this data set don't correspond to complaints. Maybe each file number should be associated with only 1 complaint, but I'm not sure about that. So I just left it the way it is, but we might want to look at this file number more carefully. And then I had a look at the, how many times each file number occurs in the data. which is given by applying the value counts function to the file numbers. And then we can count those value counts again to see how many times each frequency is observed. So this means we have 9,879 file numbers which only occur once in our data set. And then 3,654 have 2 rows in the data set, and so on. And the biggest number of rows for a file number is 8, and there are just 4 file numbers that have that number of rows in that data set. So a significant number of rows have a duplicated file number. So we should probably be looking more closely at these file numbers before doing any modeling with this data. Yeah, I don't know what the file numbers are all about, so I'm going to leave them and carry on with the other variables. But it does give us something we should be looking at in the metadata. So I was very impressed by how pandas can deal with dates. So here I'm looking at the dates when the complaints were opened and when they were closed. If we go back to the missing values, we'll notice that there are actually no missing values in the date open field, but 424 in the date closed field. So these 424 rows correspond to complaints, I think, that are still being processed or have never yet been closed. The first thing I'm doing with these dates is using the PD toDateTime function to convert them into a pandas date, because there are all kinds of cool things you can do. And then instead of just looking at the dates when the complaint was open, because those are year, month, and day, I just want to aggregate them by month so I can make some tables and graphs, because maybe the day of the month is too fine to distinguish between complaints over time. So I found this really cool DT2period function that actually does this for us. So this thing just converts a day, month, year to a month, year. And then we can plot the month and year when each complaint was opened. And immediately something interesting pops up, which is that there's nothing really before 2015. And it seems like it seems like actually they didn't start gathering this data until 2015. So didn't realize that at the beginning, but immediately becomes clear from this graph. And then we can look at the month and year when the complaint was closed, and we see, well, I'm just looking at the head of that series actually. We see that the first time almost that we see any significant number of closed complaints is January 2015. So I suspect from this that they just started collecting the data in January 2015. And for some reason they have some older cases in there, but there are very few of them. So probably, and when analyzing this data, we should start in January 2015, because this older data is probably, I don't know, maybe it came from some other system or some earlier thing, but it's probably not, it's probably different in some way. So we should be careful about that. So I said that I was just going to do univariate analysis, but when we have a month year opened and a month year closed, it's very natural to want to look at them both at the same time. So we can cross-tabulate those using the pandas cross-tab function. And what it does is it just makes a table of each month and year when the complaint was opened, and then the month and year when it was closed. We get this huge table here, and it's got some kind of diagonal thing going on where there are big numbers on this diagonal and then numbers that are slightly smaller to either side of it. But it's very hard to see because it's a huge table, and it's difficult to see when it's printed like this. So because it's a matrix, we can use this imshow function to visualize it. It looks like this, and here you can see what I was talking about. There's this pattern with this diagonal here. So what's happening actually is almost all the complaints, or the majority of complaints, are being closed about a month after they were opened. And we see that very clearly in this visualization of that cross table. In this cell, I'm just counting the NA values, and we already saw that we had no missing values for opened and 424. Oh no, we've got 424 now for closed. Okay, so that means that there are 424 complaints that are still open, and it's kind of important because if we're doing some analysis of this data, we might want to get rid of those ones. I also checked which is the most recently open one, and indeed, it goes up to yesterday. So data is being added to this every day, and obviously the cases that have been added most recently haven't been closed yet. Then it was natural to look at how long a complaint is open for. So that's the date when it was closed minus the date when it was opened. And I call that the duration. And you can just use the subtraction function on the Pandas series to do this. It's really neat. And it gives you a series of days, and then you have to apply the dt.days function to that to get numbers. And then I'm, like I had before, I'm applying a function to these because they have a very skewed distribution. And I applied this log10 function to the number of days plus 1. And the reason why I'm adding 1 to the days is because a lot of complaints were closed on the same day they were open. So they have a duration of 0. And we can't take a log of 0. So just for convenience, take a log of days plus 1 instead. It's often better not to do that. But just for exploratory analysis, I think it's fine. So the duration values, so the number of days when something was open, they're actually have quite a tight distribution, which is the same conclusion as we saw from that diagonal being very bright in that cross table there. And the average duration is about a month, like we saw before, so 32 days. This is the mean duration before taking logs, so it's not clear. I mean, there are some massive outliers here, which I haven't shown you, but it's not entirely clear that taking the mean is a very meaningful thing to do there. Just to show that the range of possible duration values is 0 days, and then the longest one is 2,449 days. Another thing we can do, because these duration values, so this is, remember, the number of days it's been opened until it was closed. These duration values are actually discrete, so we can make a bar plot of them instead of a histogram, and we get an interesting picture. So what we see is that actually there are quite a few with a duration of 0 days, and then we get these peaks at multiples of 7 days. So this is something we didn't see from the histogram, but because we actually have a discrete variable, we can make a bar plot, and it's interesting that it tends to take a whole number of weeks for these complaints to be resolved. And if I was to guess, I would expect that, I don't know, the companies might say, we'll get back to you in 3 weeks at the most, and then they're taking the maximum amount of time they can, and then the complaint is taking exactly 3 weeks. Something like that might be going on, but I don't know. I mean, it's just an interesting pattern, the kind of thing you should be looking for in exploratory analysis, but I'm not claiming that I can explain it. Another thing you can do with dates is to look at days of the week. So again, Pandas has a function for doing this. You can just do dt.weekday name, which tells you the day of the week. We can count how many days of the week we had complaint. We can count how many complaints were opened on each day of the week. And well, Wednesday is a bit higher than the others, and Friday is a bit lower. So there's actually a significant difference between Wednesday and Friday here. And also for closed, we see that very few complaints are being closed on Friday. and a very large number on Tuesday and Wednesday. So I don't know what it means, but it's quite interesting. And that's the date variable. So those are definitely the ones I had the most fun with. There are lots of things you can do with dates that are not immediately obvious, but all kinds of interesting things can be extracted from dates. So the rest of the variables we had were basically just categorical, so things like the coverage type. So we can see that we mostly had auto insurance. And then we had 69 types of coverage. This is slightly interesting because it tells us something about how the data were collected. So the fact that there are only 69 possible values for this variable means that probably the process for collecting this data is quite good, because you can imagine that somebody might just type this stuff into a computer, and it could be very messy. So they might type aviation insurance instead of aviation here or something. But they haven't done that. So we have quite a systematic grouping of possible types of insurance, and that's good to know. And then subcoverage, remember, was the one where we had mostly missing values. So I won't say too much about that. Reason, sub-reason, disposition, has something to do with what happened to the insurance claim. Conclusion. So what am I counting here? I'm counting how many complaints are missing a conclusion. So actually 378 are missing this conclusion value, which is strange because we had 424 that haven't been closed. So I would suspect that if a complaint has been closed, then it should have a conclusion. And if it hasn't, then it shouldn't. But that doesn't appear to be the case. So we should maybe investigate that further. We can look at different kinds of conclusions that have been given to us in the data set. So almost half the complaints are found to be unjustified. Only 13% are found to have been justified. And then there are various other types of conclusion you can have. Furnished information, I'm not sure what that is. We have to, again, get some metadata and find out about that. And then we have so those are all categorical variables, and we've seen what kind of things we might want to do with those, basically make a table of the possible values. And then we've got a nice numerical variable here, which is the recovery amount. So we see that because a lot of complaints were never upheld or found to be invalid, we've got a lot of zeros in here. But then we've also got some amounts of money that were recovered. And we can make a histogram of these recovery amounts, and we should see a big peak at 0. That's not a very useful histogram, so again, we can apply logs to it. And actually looks very nice. So this is a histogram of the recovery amounts that were bigger than 0, and they have a very nice log normal distribution. Often, when you're dealing with financial data or money-related data, you will see a distribution like this. It may or may not be 0 inflated, and then it will be log normal. So when you take logs, you'll get a symmetric and bell-shaped looking distribution. The final variable that we didn't look at was status, and status was it seems to tell us whether the complaint has been closed, whether it's still open, or some, I don't know what these are, reopen, do not purge, and pre-close, but there aren't very many of them. I wanted to check that this status variable was consistent with the variable that tells us whether it's been closed. And you can see that complaints that have been closed always have a status of either closed or do not purge. So that looks like those two variables are consistent. And these are the kinds of consistency checks that you should be doing, either when you're cleaning the data initially or doing the exploratory analysis. So that's all the univariate analysis. We've been through all of the variables in the data set. Now I want to see what kind of things we could do for multivariate analysis. And I'll just look at pairs of variables here. So basically, the three kinds of pairs of variables you can have are continuous and continuous, or categorical and categorical, or continuous and categorical. So when you have two continuous variables, it's fun to make a scatter plot, which I've done here for the duration and recovery variables. This is the kind of ugly scatter plot you get when you have financial data, because there are some huge values here. So we often might want to transform these, and we already saw that we want to transform the duration, so the number of days from being open to being closed, and recovery, the amount that got paid out, with logs, and then we can make a scatter plot of that. We get a nice looking scatter plot. We can see that it just looks like a blob, so it's not clear if there's any association between these variables. I highly recommend not plotting a scatter plot like this with an opaque color, because often it will obscure things that you might want to do. So you can get something nicer if you use a semi-transparent color, and you can do that by specifying a color as a tuple with an alpha value, which is this number here. So this says, plot my scatter plot, but the color is going to be 0 red, 0 green, 100% blue, and a transparency of 0.05, which makes the points transparent. And if we do the same thing with the transparent points, then we can see that actually there's much more going on in the scatter plot than it looked like. So I always recommend doing this, because it gives you an insight into the distribution of your two variables. We can see some sort of vertical lines here, and those are occurring because in the duration variable, remember, we had a peak at each multiple of 7 days. And so that's why there are these lines here. And then also, we can see that it looks like there's some positive association between the duration and the payout, which kind of makes sense, because I would think it's quite likely that complaints that have been open for longer will end up getting paid more, because maybe the insurance company, when they're finally paying out, they want to compensate the people for the amount of time they've been waiting. So you can do a linear regression to see, look at the association between these, but there's a strong positive association, which was not at all apparent from the previous scatter plot. And then we already looked at a pair of categorical variables, because we made a cross table of opened and closed month. Then we can also look at continuous and categorical, and usually the initial tool for looking at a pair of variables, so one is continuous and one is categorical, is to make side-by-side box plots of the continuous variable for each value of the categorical variable. So here, an example of something you might want to look at is to take the top 10 most complained about companies, which I've selected here. I've actually got 11, because I forgot that, again, we're indexing starting from 0. And then, or maybe I've got 10. I don't remember whether the 10 is included or not. Maybe it is 10. Anyway, so we take these top companies, and then we just take the companies that are in these top 10 companies and for which there was a positive recovery amount. And then we make a box plot of the recovery amounts, and we take the logs of those recovery amounts to get a nice box plot. And I want to compare it across companies. And then I have to also use this line, because by default, the axis labels are in a horrible place. So this shows for the different most complained about companies, the logs of the recovery amount. So this would be $1,000 here and $100 and so on. The rule of thumb when looking at box plots is that if the boxes overlap, there's probably not a significant difference. And we see here that there doesn't seem to be any relationship between how much a company has complained about and how much the payout is. It seems like the payout is quite uniform across companies, no matter how much people complain about them, which is the kind of interesting thing that you might want to look at here. And then that's the three kinds of things you might do for bivariate analyses. And then you might want to look at more variables. And when you have a large number of variables, you can start using dimension reduction techniques before you visualize them. Because if you want to visualize things in more than 2 dimensions, it becomes 3 is okay, but more than that, it becomes a bit difficult. You can use colors and other kinds of things. We haven't got 3 or more categorical variables here. 3 or more numerical variables in this data set, so I can't show you an example of using PCA directly. But if you have, say, 10 or fewer, you can just do side-by-side scatter plots, which in Seaborn you can do using the pair plot function. So I'll share this Python notebook with you so you can see all the different ideas that are in there. And that's all I wanted to do for the EDA, this data set. And then I have a final slide here. So if you want to see another analysis of this data set, where I got it from was the RPubs, and it was analyzed by somebody called Jasmine Dumas. The analysis is quite different from this one, actually. But you can see another idea for analyzing this data. And then if you want to look at the original book on exploratory data analysis, that's Tukey's book from 1977. It's a very old-fashioned book. It's all about how to do things with a pencil and paper, because they didn't have very good computers. But it's also got a lot of interesting analysis. And if you ignore a lot of the pencil and paper stuff, it actually has some good advice. So I'd recommend just taking a look at it. I wouldn't recommend reading it from cover to cover. If you look at the write-ups by Kaggle winners or highly placed Kaggle competitors, often there's a lot of EDA involved in those competitions, so I would recommend reading those to get an idea of what kind of exploratory analysis you might want to do. And then a great article on using EDA to solve a problem is this Singaporean rogue train thing, where some people in Singapore were trying to track down something bad that was going on in the railway network, and using some clever data analysis without any modeling of any kind, just making graphs and things, they were able to solve this problem. And it's incredibly impressive. They made a really nice blog post about it, and that includes Python code for what they did as well. So I highly recommend looking at that. Last thing I wanted to say is when people are writing up their exploratory data analysis, they probably won't include all of the steps, because there's a huge amount of stuff that you have to do, and a lot of it is not very interesting. So I strongly recommend that you don't take whatever you see there as gospel. You actually at least look at the individual variables when you're doing EDA. And in your final report, you don't have to put everything you did, but you have to at least be confident that you haven't missed stuff. So that's my advice. And that's everything I wanted to say. Thank you for listening. Oh, you want me to turn off the recording? Yep.